Hello and welcome to one more day of the Advent of Code 2022. Today, full disclosure, I have read the statement before starting the recording of this video. As you can see, it took me some time to get to my computer. So this morning, I read the statement. I have been thinking a little bit about it during the day. I haven't coded a single line. So I play with a little advantage today. Summarizing what this statement says, it has a string, I think it says, which has a head and tail, which move, and they like to be attached, right? So when the head moves to the right, the tail follows. So it stretches one position and then they follow. The special case is when they move in diagonal, so this is a valid position, but when the head moves, then the tail moves also in a diagonal, okay? And the input has this, is a list of instructions, right, up, left, down, and the number of steps it takes. So the head is moving and you have to see where the tail goes. In the end, you can check how many positions the tail has visited, how many different positions. Okay, so if we get the input, okay, it's a pretty long input, as you can see. Let's copy this. Today is day 9, so we're pasting this. And now, this is the way I have thought of solving this. So, as you can see, well, we want to know the visited positions, right? So what we can do is have a set, and then we print the length of visited. What we're going to do is we're going to have the head position, which is initially 0, the tail position, which initially is 0, and we're going to count these v-dimensional positions using complex numbers. This is a very useful trick. So for this, we can have a list of directions. Let's have a dictionary, in fact. So what does it mean to go left? Well, to go left is to go -1. To go right is to go 1. To go up is to have -1j. This is where the complex numbers kick in. And to go down is to go plus, sorry, I forgot a colon here, is to go 1j down. So these are the different directions we are taking. So what we're going to do now, we're going to simulate each of these movements. So for line in open, we'll start with the example, I guess. So num.x. This problem can be a little bit tricky to debug, I think, if we don't get the right solution. So the line is the direction and a number of steps. Line.split, strip split, and the steps are an integer, of course. So steps. Okay, so what do we want to do? We want to do for I, or I think we don't need this variable, in range steps. What we're going to do is we're going to simulate this step. So first we need to move head, then move tail if necessary. So that's what we're going to do. So how do we move the head? Well, the head moves in the direction of D. So now we are changing the head. It is either going 1, -1, or I, or -I in the complex, in the imaginary axis. So then, how do we know if we need to move? Well, we need to move if, let's say, let me just open this playground that I like a little bit. So if you do 1 plus 1j, this is a complex number. So if we call this number this, you have the real and the, image. These are the real and imaginary parts of the number. These are properties. So what we want to do is if the h dot real minus t dot real, if the absolute value of this is larger than 1 or is equal to 2, or the same for the imaginary numbers. So if the image and imaginary part is larger than 1, then we need to move. How do we move this tail? Well, we move this tail in the direction of the head. So what we need to do is we need to sum the h dot real minus t dot real. That is what we need to sum. But this difference could be 2. And we never move 2 steps. We always move 1 step. So what we need to do is we need to divide this by the absolute value of real minus t dot real. This way, what we're doing is we are moving only 1 step. And we're moving 1 step only if this difference is larger than 1. So if if this is greater than 0, right? Otherwise, we don't want to be doing that because we're dividing by 0. So for sure we can later. And the important thing is that this is done in the imaginary axis. We can have some problems if this, because these imaginary parts are float numbers instead of integers. So we'll see. What we want to do then is we visited.add tail. Okay, let's see. Let's edit the 9.example. Let's edit this example and see what we get. Sorry. I also added this handy command which runs the program directly. 13, is that the solution? Apparently yes. So I don't know, before doing any more debugging, let's try to run with the input. And we got the gold star. Okay, that was a very quick solution. It was very helpful. It is very helpful that I had read this statement beforehand. Let's see now, because I haven't read the second part. So let's see the second part. A road snap. Suddenly the river is getting a lot closer than you remember. Blah, blah, blah. Rather than 2 knots, you now must simulate a rope consisting of 10 knots. Okay. 1 knot is still the head of the rope and moves according to the series of motions. Each knot farther down the rope follows the knot in front of it using the same rules as before. Okay. Using the same series of motions as the above example, but with the knots marked H, blah, blah, blah. Okay, that's interesting. So then the solution is, how many positions does the tail of the rope visit at least once? Okay. That's an interesting change. So what we want to do is we have 10 knots. So tail 9. So from 0 to 9. So let's see. Maybe we can just copy this and have it in the difference. So this is HT. So we can have knots equals 0 times 10. So we have 10 knots in the 0. So what we are doing, first thing we do is we move the head. So instead of moving the head, we move the knots 0 is moved in this direction. And now we need to move, instead of moving the tail, move each knot if necessary. So we can say for I in range 110, so the next 10 elements. Here we could say the head is the previous knot, right? So knots I minus 1. And the tail is knots I, right? So when we do this change here, what we do is the nodes I equals the tail. What I'm doing here is just reusing the same function we did, and then we add to the visited the nodes -1. So what the last node did. Let's run this. Okay, let's run this with the example. Well, let's just submit this, just in case. Okay, we got the gold star. So today we were very, very, very quick. I think, of course, I had read the statement before, but I think the solution we found is very useful. It's very interesting. So what we can do now, we can refactor this code, but I think we can finish. I always say we finish quickly, and then it takes me a lot of time. But what we want to do is we want to do the following. First, we're going to read the input. Right, so read input. This is of course something we should do. So what we're going to do is let's say instructions are a list of for line in open 9.in. Let's first copy this. Let's copy these outputs, because this is what we want to assert. Assert len of visited equals this. We copy this value. Okay, so now if we don't have any output, it's because this worked. Okay, so now we're going to read the input. So, or moves, let's say, what are the moves? We're going to have line.split or line 0, so the first character, the direction, and then int of line. We could do this, and it should work. So let's print the moves. Make sure, yeah, it looks right. So what we have here is it is for the steps in moves, and we can forget about this. Okay, so we have this. It seems pretty obvious that we can, if once we have solved the second part, we could solve the first part with the same function. We could have a def visited. Let's say this is a function for which we send a list of moves, for example, or even not even that. We set the initial, the nodes. Let's see. So we could just have this function here. Of course, we can just take this here. We have this visited here, and visited, let's call it. Return. We're going to, right now I'm just trying to remove some code. And here, what we want to do is n visited of 0, 0 is this. Let's remove all of this. Okay, list index out of range. Oh, for I in range 10. So we could say for I t in range in enumerate nodes. No, forget about that. In range len of nodes. Okay, so now n visited is this, and we could say n visited 0 times 10 equals this. Delete till the end. Okay, so now we have this code. We already have this. This is part 1. part 2. So we could say, well, this is 0, 0. So there's only two nodes, and there are in these positions 0 and 0, and then here there are 10 nodes, all in position 0. Right? So this is good. We have read the moves, and here we have this this function. I mean, even though we can be, well, let's see. I mean, n visited, I think it's better to return the visited points, but let's stick with that for now. So what do we do? First, we move the head for each step, then move its not if necessary. So here we have this absolute value of the real. This condition is the same as this one, I think. Exactly. And I think this is a more strict condition, so I like it better. This larger than 0, let me confirm. Exactly, we got a division by 0. So this we need, for now at least, for having this division by 0. So now how could we simplify this code a little bit? How could we simplify this? So we have this. If the distance is 2, we could have a distance function, but we only use it once, so maybe it's not really necessary. So for each move, direction, steps, move head, we first move the head. Maybe it is not necessary, but and move it's not if necessary. So here we are for I in range. There's another way of doing this. So which is for ht in zip nots 1 till the end. Sorry, knots and knots 1 till the end. Is that right? Or we could do this. The problem is that we need to modify the knot here. So it is not exactly this. We would enumerate this and then have an I. See if this works, and then we would have I plus 1. Syntax error. No, there's something wrong here. We are taking heads and tails from the first knot, zipping with the starting with the second. And we take the I. Oh, sorry, I need to remove this. Okay, now it works. So this is a way of simplifying this. So we are iterating through heads and tail. We keep this integer to modify this knot later on, because if we just modify the t, that doesn't work. It's not modifying the list. We need the index to modify the list. So, and then we can add the, we add the last one. The final tail is what we are adding to mark tail as visited. So what else can we do? Well, let's check at these conditions, right? So here what we're doing is we're moving the tail or the follower, the following knot. We're moving it if the difference between in one axis is 2, either for the real axis or for the imaginary axis? Okay. And then we're moving it one unit in its axis. This is the way we do this. So here, what we could do, instead of doing this, I mean, this condition is a bit weird. This is the same as saying h.real is different from t.real. And this is the same of saying h.image is different. I think this is definitely more clear. So if there's a difference here, we change this. If there's a difference here, we change this. The amount that we change it, we need to move in the head's direction. So we do head minus tail, and we divide by the absolute value, so we get the unit. And the same we do here. Move its not if necessary. I don't know. I think this is pretty good. This is pretty good. Of course, one thing that I always have the temptation of doing things in a functional way. I don't know why, but I like that. But I think this time I'm going to try to limit myself from doing this in a functional way. What would the functional way be? So we could have some kind of function that returns the list of visited nodes, which we could do with some kind of accum function. But maybe one thing I'm not sure I like is having these nodes as an uppercase variable. So what did I do? Forget this. I mean, this is a parameter in a function, so we don't need to have it uppercase at all. Here, h and t, I think I'm going to substitute this. I don't usually use these uppercase variables in my code. Sometimes you won't if you're reusing well, in this case, there makes sense because these are this is a global variable, it is a constant, so it makes sense that it is uppercase. But if these are some parameters or some just variables we are taking here, it's not necessary. Okay, so what we are doing here is we are adding the real part if we're moving in the real axis if there is a difference. We're moving in the imaginary axis if there's a difference. I think we can just simplify this and remove some, sorry, not ik, ij, sorry, 1j. So this is, we can remove this parenthesis. So we move it and we add it. Should we do that? Well, that also makes sense because we're only modifying this inside the if, which is when it changes. So we don't need to add this. Oh, sorry. Yeah, we only modify this not I if we're inside this if. So we can do that. Again, this is a stricter thing to do. This only changes. We only change t inside here, so we only modify this not here. Mark tail as visited. Should we do that? We should do this here. So this for loop I don't like this I, having this, doing this I plus 1 seems a bit, can be a little bit hard to understand, but I don't know if there's a better way. So another thing we could do, let's put this apart or not. So another thing we could do is we could use, we could say positions visited by tail, and here we could yield knots -1. So here what we want to do is, instead of doing this, it would be positions visited by tail, length of set. Why would we want to do this? Because instead of having n visited, which seems like a bit of an ad hoc thing to do, when doing this, we give it a name. So the variable, it's not n visited. N visited what? What are we visiting? Are we visiting, is it what the head visits? Is what the tail visits? Is what any node in the row visits? So this is a clearer thing to do. So positions visited by tail, even we could call it tail positions maybe, which is shorter and it's also true. And we yield, we could add a comment, so yield tail position. So now we are doing for each step. Of course, we could also have the moves here. It's not necessary, we can just use the global variable. So we move the head, first of all. Move the head in direction D. Then we move each knot if necessary. So we're iterating through each knot, heads and tails. If this difference is equal to 2, then we move. We move in this axis if they are different. We move in this axis if they are different, and we save it here. We could also, remove one line by doing this. Knots I plus 1. We have removed one line, but it was more clear, right? When it was T instead of knots. I'm not sure if it was more clear or not. We could also say knots I plus, let's undo this and have an alternative function. So it would be knots I plus 1 equals, so it equals T plus this if h.real is different to t.real plus and else 0. And here it is this. If h.image is different to t.image, else 0. Okay, so this, well, you already see that with the formatting, it is much longer. And also, generally, I think it's definitely less understandable. So I think we don't want to do that. So we're back to where we were. I only have the question if we should be adding this to the tail or we should be adding this to this. So here, let's update tail t well, not, it's not the tail, it's the knot that we are visiting. So one thing we could do instead of, so H and T is very helpful. Could be confusing. We could also have a pref and not, something like that. So it is clear which one is which. But I think I'll stay with H and T for heads and tails. Okay, so I think we got to the destination. We got till the end. I think this implementation I like very much. It is pretty understandable. It is short. It was very quick to code. I'm happy that I had read the problem before, so it was very quick to implement. But yeah, my understanding, my idea of what I wanted to implement really fitted. So as always, let's comment on the lessons learned. I guess the most important one is that we are use complex numbers such as 1 plus 1j to represent coordinates in a grid. So that is useful given a complex number, so as this one here. We can use c.real, we can use c.image to get the real component, to get the imaginary component. And we can use this -1, 1, -1j, 1j to represent all these movements in these directions. What else did we use in this? Well, we used the abs built-in function, which is the absolute value. We used the zip, enumerate, and range. So one trick that we use is to iterate consecutive pairs in a list. So imagine you have a list 1, 2, 3, 4, and you want to iterate through 1, 2, 2, 3, 3, 4. What we did is use this trick. So the enumerate is optional. So let's say this is pref next, let's say. So we use this zip of the list, and the list is starting with from the first element, and you get this kind of pairs, pref next. What else did we do? Well, we used yield again, which is create a generator function, or make a function a generator. So this function is now giving lists of nodes with this yield statement. And finally, well, we used sets. I don't know if we could say this is a lesson learned, but we used sets. We use sets many often. Well, we use this trick also, which is interesting. Initialize or create a list of 10 equal elements. There's a caveat to this thing. If you wanted to do a list of lists, let's say 1, 2, 3, and then you want to have 10 times this, you need to be very careful, because this doesn't have the usual intended outcome. If we did this, list equals this, okay, this is what you expect. But if you take the first element in the first list and you assign it a 5, then all of the elements have been updated, because this is a list of lists, but this multiplier is copying exactly the same list. So these are 10 references to the same list. So this is generally not what you want to do. If you want to do that, what you would do is do this for in range 10. You use a list comprehension. Sorry, you need to close it. And now this looks the same. But when you do 0, 0 equals 5, and you check the list, only the first element is modified. usually you want to do this. Okay. Okay, this is not a lesson we learned in this problem, but this is something that we need to take a lot of care on with Python. What else did we do? Well, this is a bit of, I don't know if you could consider this math, but we use this trick here, right? So to get a unitary vector in one direction, this is not even a vector. Well, I mean, it is only in the real part, but we use this to move one unit in the real direction. Okay, so that was useful. So what we imagine, this will have a value of either -2, 1, sorry, -2, -1, 1 or 2. If you divide by the absolute value of this, you will convert the 2 to a 1 and the -2 to a -1. So by applying this function or this division, you're converting -2, -1, 1 or 2 to either -1 or 1, which is what you want. And I don't know if there's anything else worth commenting from this problem. Let's leave it here. I hope you enjoy it, and let's see you tomorrow.